Okay, hi guys. So today we are finishing off chemical equilibrium. So we're going to start off where we ended yesterday and then hopefully finish with a past paper, and you should then be okay with chemical equilibrium, I hope. Okay, so yesterday we ended up on this graph, and I was trying to explain to you what happens at the 20-second mark and what happens at the 35-second mark. So I'm just going to open it on a whiteboard so I can write on it and show you. Okay, so over here, at the 20-second mark, which is over here, there's this steep decrease that you get from your products, your HI. Okay, and that steep decrease shows us that it means it had to be removed. So this was removed from your system. And when it is removed from your system, it means that your reaction is now going to shift in this direction to kind of replenish that loss that you had. So if you look over here then, for a few seconds after the 20-second mark, your reactants decrease as well. And then over here, the products are increasing as the reactants are decreasing until you reach equilibrium over here again, so it's stabilized. So the change was you had a decrease in your products, which was your hydrogen iodide. That caused your forward reaction to be favored. And once your forward reaction was favored, it decreased the reactants and slowly increased the products again. And then you went into chemical equilibrium. Then over here, there's a change again, but this time there's a change on both systems. Okay, so when we look at it, both your products and your reactants are decreasing, which tells us it can either be a catalyst or temperature. So in this case, you now have to look at, is there an even change for both of them? Is there an equal change, or is there different? So if you look at it, your products decrease 1, 2, 3, about 5 blocks, okay? And your reactants increased about 1, 2 blocks, okay? So that means immediately we know it cannot be a catalyst, because a catalyst would have given them an equal change. And that means as well that because there is a decrease in temperature and your products are decreasing, it means that your reverse reaction is being favored, sorry, because there are more blocks that are being decreased. So at this point over here, the reaction is going that way. Okay, does that make sense to everyone? Do you see how we actually end up determining whether something is a concentration change or a reaction change? I mean a catalyst or temperature. So at your 35 seconds, which was over there, where both of them decreased, there was a change in your temperature. Our products decreased more than the reactants, and that told us that the reverse reaction was favored. If it was the other way around, if your reactants had more blocks that it was increasing than the products, it would have been your forward reaction that was favored. Okay, then they give us this graph and they ask us to determine the equilibrium constant for the system at 17 degrees. So they're basically asking us to look at the graph and find our concentrations and then work out our Kc value. So let me just go back to the whiteboard. Okay. Okay, so they give us this, and they have now asked us for our Kc value. Oops. Okay, so your Kc value, which is equal to products divided by reactants. Our formula is given here. So we can go and say it's going to be the concentration of CO, Cl2, and divided by carbon monoxide times chlorine. Okay, then we have to go onto our graph and we have to go read off the value. So we're looking for 17 seconds. So it'll be roughly somewhere here. Okay. So we're looking at these points. So first we're going to go there. So to me, the blue line looks like it's about 0.6. I can write it there. Okay. If we go up to the black line, it looks like it's about halfway there. So that's 0.75. And if we go up to the red one, it's going to be roughly there. So 1.75. And then we just go and substitute those values in. So it'll be your black line concentration, which is 0.75 divided by 0.6 times 1.75. And that gives you 0.7142 dot dot. So we round it to 2 decimal places, and it gives us 0.71. Yes, the chat function is on private because of the fact that we don't want people to say rude things. Mpilo, no one has asked a question yet, so if they do, I will read the question out loud and tell you what they've asked. Okay, so does this make sense to everybody? If they ask you to work out the Kc value and they give you a graph, then you literally just go and read the values off the graph. With these type of questions, they will give you a range because of the fact that, like in this instance, you can't see 100% where values are. So there'll be a range that they give you for you to get the right answer, unless it is at a specific point where you can actually see the exact number. Otherwise, they'll give you a range. So they asked us for the Kc value at 17 seconds. So you go onto your graph, you find 17 seconds. I said it should be around about here. And then I just go and find my values. So what my concentration will be at this point for each line. And then Kc value is reactants over products. So I write what my Kc value would be. And then I go and look for my values. I plot my values in, put it in my calculator, and I find my answer. So I was just asked to re-explain that. Okay. So what these graphs should have shown you is the following. Concentration time and mole time graphs show you that if there is a change in concentration of a substance, it would appear as a sharp increase or decrease. So like with the one where we had the hydrogen iodide that was taken out, there was that sharp line, but it was only for one of the reactants or one of the products. And then there will be a gradual change after that. So like I explained, then suddenly your reactants were trying to put back product, and then it slowly eased back into the graph. If there's a change in temperature, it will affect both of your forward and your reverse reaction. So the way we know that it's temperature though is the one will be affected more than the other. So thinking about that graph with the hydrogen iodide, the products had a steeper curve than the reactants, so we knew that the products were being. So someone just asked, so the product concentration are always multiplied and not added in Kc? Yes, 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 yes. Kc value, we never add anything. You're always going to multiply your products and you're always going to multiply your reactants. If you do add it, they'll actually deduct marks because you shouldn't be adding it. So they're always being multiplied. Then on your graphs, if there's a change in pressure, then it would almost look like a concentration one. where there's the sharp increase or decrease, but it's in all of your reactants or all of your products. Okay, because remember, when you're increasing pressure, you're increasing it on the whole system. And when you're decreasing it on the whole system. And then the last thing is when you add a catalyst to your system. So adding a catalyst increases both the forward and the reverse rate in the same manner. Because remember, a catalyst goes and it decreases activation energy. So both of your reactions will increase, and they will increase in this with the same amounts. And that is how we distinguish between a temperature and the catalyst change. The catalyst increases both the same way, its temperature only increases one more than the other. Does that make sense to everyone? I hope so. Okay, then I just quickly want to show you what they could ask you in an exam paper. So this was out of the 2017 paper, if I'm not mistaken, or 2016. And the question goes, you've got hydrogen gas. It reacts with sulfur powder according to the following balanced equation. So hydrogen plus sulfur gives you hydrogen sulfide. And then they tell you the reaction is less than 0, the delta H, so it means it's exothermic. And they tell you the system reaches equilibrium at 90 degrees Celsius. The sketch graph below was obtained for the equilibrium mixture. And then they say a catalyst is added to the equilibrium mixture at T1. Redraw the graph above in your answer book on the same set of axes. Complete the graph showing the effect of the catalyst on the reaction rate. So if you guys had to venture a guess, what do you think is going to happen to our graph? Any ideas? Let me just make it bigger so you can all see. Okay, so remember that your catalyst goes and it's going to increase both of your reactions. So first, let me just do the forward reaction. It increases it, and then it reaches equilibrium. And then your reverse reaction, it increases it, and then it reaches equilibrium. So yeah, okay, you have a sudden increase for both of them. Okay, and the keyword here is that both of them have that sudden increase, exactly the same way. And then over here, after you've added the catalyst, you've got a constant rate again. Okay, so when a catalyst is added, you've got this steep increase, and then it will go into a constant rate again. Both of them increase the same amount, and both of them level off again. That is how a catalyst works. Does that make sense to everyone? Anyone have questions? Okay, then I'm quickly going to leave this here for 5 seconds so you can all have a look. This is a homework question. So I'm going to upload it onto the Google Drive after this lesson, and you can all have a look at it. And then I will also upload the answers to it. But this is the type of question that they ask based on rice tables and all of that. And hopefully by now you should be able to do it. Okay. So like I said, I'll upload it onto the drive after this lesson, and you can all attempt it. Okay, so basically after these 2 lessons, you should be able to do the KC values now. You should be able to use a rice table, and you should be able to interpret the graphs. So I'm going to work through the November 2015 past paper, question 5 and question 6, which is based on rates of reactions. Let me just, sorry, I just want to put it on a different screen. Okay. So question 5 goes, sorry, my screen just stopped sharing, I don't know why. Should be fine again. Okay. Okay. So question 5 says you've got a dilute acid indicated in the table below. It reacts with excess zinc in each of the 3 experiments to produce hydrogen gas. The zinc is completely covered with the acid in each experiment, and then they give us the 3 different experiments, and they tell us the volume of hydrogen gas produced is measured in each experiment. So question 5.1, they tell you, name 2 essential apparatuses needed to determine the rate of hydrogen production. Okay, do you have any idea how we will determine the rate? How do we measure rate in rates of reactions? What is the formula? What do we need? Any ideas? Okay, so the first thing that we're going to need is time. And how do we measure time? Using a stopwatch. The second thing that we're going to need is a way to catch up the volume. So if you add an acid to zinc, so the general rule is acids added to metals will always give you hydrogen gas and then a metal salt. So we want to catch up the gas and see how much of the gas was made. So you would be able to use something like a gas syringe, or you can use a urette, but I would stick with a gas syringe. It's the easiest way to do it. Does that make sense to everyone? Okay, then they tell us the graph below obtained for experiment 1. So if you go look, experiment 1 is 100 cubic centimeters of 0.1 moles per decimeter cube sulfuric acid that was added to your zinc. And they say use the graph to answer the question that follows. So then the first question they ask you is, at which time T1, T2, T3 is the reaction rate the highest? So I quickly want to show this to you visually. Let me just, there it is. Okay, so what they're basically asking you is at which point over here do you have the steepest curve? Okay, so if you look at this graph, I don't know why I just did that. Okay, sorry. I don't know what's doing that. So if you look at this graph, you can draw a straight line over there and the straight line at T2 and a straight line at T3. And imagine that these were straight lines that we were drawing to go through our y-axis, and we can go work out their formula based on maths. Y, your normal slope formula, so m is equal to delta y over delta x. So this question over here, where they're asking you reaction rate is the highest, they are asking you which slope is the steepest. That's what they're asking you. And in this case, it will be the red one. Yeah, I just can't draw a straight line, but it should be at this point over here. So for this answer, we would write T1. Does that make sense to everyone? So the highest reaction rate would be at T1. It has the steepest slope. Okay, then they're asking you, using this graph, answer the following questions. At which time T1, T2, or T3 will the mass of the zinc present in the flask be the smallest? So they're basically asking you, where has most of the reactants been used up? That's what they're asking you. So where has most of the reactants been used up? So if you look at the graph, it is going to be here at the top point, the point where you're starting to curve off. That is where most of your reactants would have been used. So the answer here would be T3. Does that make sense to everyone? You guys are a quiet bunch tonight. No one's responding. Okay. Then they ask you, looking at this graph still, in which time interval between T1 and T2, so over here, or between T2, Zakanya, do you want me to repeat 5.2.2? So the question was asking you, where do you know that the zinc, the mass of the zinc present in the flask is the smallest? So they're basically asking you, where has most of the reactants been used up? If you look at this graph, okay? So looking at this graph, you're looking at your products being made. So you're looking at your hydrogen gas being made. So you start off with 0 hydrogen gas, and then it starts increasing, okay? So that means over here where you've got no product, that's going to be where your reactants are the greatest. And then as your slope increases, your reactants are decreasing because your products are increasing. So your reactants are being used up. And then you get here to the top at T3, where they kind of level out. And at T3, at that point, before you reach equilibrium, where your system's going to now have a reverse and a forward reaction happening at the same time, you have used up most of your reactants and they haven't been replenished yet. And that's why it's at T3. Does that make sense? Okay. Then for 5.3, it says in which time interval between T1 and T2 or T2 and T3 does the largest volume of gas form per second? So once again, if we think about it using your slope, they're now asking us, is it between this and this point? So you draw a straight line connecting them. And I can't draw, sorry. Let's do it again. Okay, like that. Or is it between T2 and T3? And you draw your straight line between those 2 points. Once again, using your m is equal to delta y over delta x formula. Okay, you will see that the difference here is much greater than the distance over here. So your red line is steeper. And because your red line is steeper, that will be the interval in which you have the greatest gas being formed. So this answer would be between T1 and T2 because the line is the steepest. Okay, so when they ask you questions like these, always look at straight lines. Think about your slope and how your slope is changing. Then in question 5.4, they ask you to redraw the graph for experiment 1 in your answer book. On the same set of axes, sketch the graph that we'll obtain for experiments 2 and 3. Clearly label the 3 graphs in the experiment. Okay, so I am just going to take this and just put it into so that I can draw on it. Okay. Okay, so we just need that to see what happens in the experiment. And then I'll just redraw what the graph would have looked like. So if this was the graph, and that was experiment 1, and then you had your T1 and your T2 and your T3. And now they're asking us to draw in experiments 2 and 3 as well. Okay, so Masefa is just quickly asking, the greater the something, the steeper the slope. If this slope is steep, then it means your rate of reaction is quicker. It means that you are increasing the concentration of your product or your reactant more. So that's what the slope indicates. Okay, so just quickly to see the difference for experiment 2, you've got 50 cubic centimeters, where in experiment 1 and experiment 3, you've got 100. And then for experiment 1, you've got 0.1 moles per decimeter cubed, and for experiment 3, you have that. But for experiment 2, you've got a greater concentration. Okay, so what that means is, because you've got a greater concentration, double the concentration than in experiment 1, and you've got half the volume. So here you've got half the volume, but you've got 2 times the concentration than experiment 1. It means that your curve is going to look slightly more increased, and then it's going to go to where your experiment 1 is over there. So it's slightly steeper for experiment 2 because you have double the concentration, but then it eases off and it goes to the same point as experiment 1. Then for experiment 3, it looks exactly the same as experiment 1. The only difference here is the acid that you're working with. Okay, so in experiment 1, you're working with H2SO4 or sulfuric acid. And what that means is you have 2 protons that can be made. So you've got 2 H's that you can have. Whereas with hydrochloric acid, you have 1 proton that can be made. So if I was to write it in a formula happening there, you've got zinc solid plus H2SO4, and that will give you your zinc salts plus your H2 gas. So that's experiment 1. Okay, for experiment 3, you still have zinc, but you now have hydrochloric acid. So you will have zinc chloride and your hydrogen gas. And you need to quickly balance your reaction. So there's a 2 in front of this. So the important thing to notice here is your zinc and your acid has a 1-to-1 ratio. Okay, whereas with hydrochloric acid, your zinc and your acid has a 1-to-2 ratio. So what that means is you will need double the hydrochloric acid than you do the sulfuric acid if you want to get the same curve. So what will happen is your experiment 3 will look like this. It'll have half of the graph because of the fact that you have the same volume for both your sulfuric acid and your hydrochloric acid, and you've got the same concentration. But in order for it to bond with your zinc, you need double the amount of hydrochloric acid. So that is why you only have half of this curve. Does that make sense to everyone? So when they ask you a question like that, you always have to go look at your ratio between your metal and your acid. what the ratio is, and then that will tell you how your curve will change. Because it's half the reaction basically occurring, your curve is halved. So I hope that makes sense to everyone. Okay, so then question 5.5, they're asking us, how will the mass of zinc, oh no, sorry, I jumped the gun. It says the initial mass of zinc used in experiment is 0.8 grams. The balance equation for experiment 3 is zinc plus 2 HCl gives you zinc chloride plus hydrogen gas. And then 5.5.1 says calculate the mass of zinc present in the flask after completion of the reaction in experiment 3. Okay, so let me just do that. And then go back to the whiteboard. Okay, so they're asking you that, and just remember that your HCl concentration was 0.01 moles per decimeter cubed. And there was 100 cubic centimeters in there. No, wait, that was 0.1, sorry. Let me just fix that. Okay, so 0.1. And then they tell us the mass of your zinc is equal to 0.8 grams initially. Okay, so first things first, we can go work out the moles of this. So C is equal to N over V. We have the volume, we have the concentration. So 0.1 is equal to N divided by 100 times 10 to the negative 3. Remember that your volume needs to be in decimeters cubed and not centimeters cubed. That's why the 10 to the negative 3 is there. So then you get your moles to be 0.01. And then we need to go look at our ratios. So remember that I just told you your zinc to hydrochloric acid ratio is 1 to 2. Okay, that means that when it reacted, then your moles of zinc would be half of that of your moles of HCl. Okay, so we can then say that N moles of zinc is equal to 1/2 times the amount that we had here, 0.01. That should give us 0.005 times 10 to the negative 3. Okay, so now we have the moles. So we say that the reactant mass is then going to be your NZN times your molar mass, which is 5 times 10 to the negative 3. and you multiply that with 65 because that is zinc's molar mass on the periodic table. And that should give you 0.325 grams. Okay, so that is the mass that reacted. And they tell us that we initially, though, had the 0.8. So what are we left with? So mass final is going to be your initial minus reacted. So that is 0.8 minus the 0.325 grams. And that should give you 0.48 grams. Okay, does that make sense to everyone? Hope so. So then question 5.5.2, they ask us how will the mass of zinc present in the flask after completion of reaction in experiment 2 compared to the answer in experiment 5.5.1. So what is happening when experiment 2? You still have sulfuric acid and you now have zinc. So your ratio of zinc to H2SO4 is gonna be 1 to 1. Okay, so that means that it will be smaller then. And the reason it will be smaller then is because you've got a 1 to 1 ratio. It means that more of your zinc is going to react with the sulfuric acid, and when more of the zinc acts with the sulfuric acid, you will get a smaller amount. Does that make sense to everyone? You'll be left with less zinc because more zinc is reacting. Yes? Okay, I hope so. Okay, then the next question, they tell us an unknown gas, X2, is sealed in a container and allowed to form X3 gas at 300 degrees Celsius. The reaction reaches equilibrium according to the following balanced equation. And then they give you the equation, and then they say, how will the rate of formation of X3 compare to the rate of formation of X2 at equilibrium? So that's a trick question. They are basically just asking or trying to see whether you understand that at equilibrium, the rates are equal. So you just say equal to, they're at equilibrium. Okay, and then this is the difficult one. They tell you the reaction mixture is analyzed at regular time intervals. The results obtained are shown in the table below. And then they give you these results and they ask you to calculate the Kc value. Okay, so I'm going to calculate this Kc value, and there is still a bit of this question left. So before I finish, I quickly want to find out, do you guys want me to complete this tomorrow in class, or do you want me to start with electricity like we had agreed upon last week? And then I can put the answers explained onto Google Classroom for you guys in the folder. I mean, on the drive, sorry. Quickly, just give me some ideas what you guys want, because I don't mind the latter, meaning okay, so most people, it looks like the verdict's in. Most people want me to just complete this onto a Google Drive doc, and then you guys can try it yourselves. And then tomorrow I will be doing electricity. Is that the verdict? It looks like that's what's coming through. Yes, okay. Do you all have the link, the drive for the link to Google Drive? Okay. So I can't give the link to everyone right now. I just realized that because we're all on private. I'm going to ask Ms. Vermeulen to send it out to all of you. You all have signed up, so she will know. Ghana, okay. Give me a sec. Let me quickly get it. Okay, so let me get that. I will give you the worked out problems for everyone, so just hang tight for 5 seconds. And then tomorrow we will start with electricity. Okay, so I'm going to give you guys the link, and like I said, I will give you the worked out problems with explanations so you can all try it yourselves. And then okay, so there's the drive link. Have a look at it. And like I say, all of these worksheets will be on there with explanations. If you still don't understand, just send an email. And then tomorrow we will do electricity. Okay, I'm going to start this question. Let's see how far we get, so that you at least know where to start with it. Okay, so we're going to work out the Kc value. Okay, so your Kc value, if you look at your graph, you'll see at this point over here, between seconds 6 and 10, you now have the same value. So that is the point when you have reached equilibrium. So Kc is equal to products over reactants. Our product is x3 to the power 2. You divide it by the reactants, which is x2 to the power 3. And then you get its values off of here. So this is my x2, which are my reactants. So this is where I have reached equilibrium. So I'm going to say 0, 0, 6 cubed. And for x3, it's going to be 0, 226 squared. And if you plot that into your calculator, you should get an answer of 236.46. Okay, so that's obviously a huge number. So that means that you have a lot more products than you do reactants. So question 6.3 will then ask what's going to happen if you increase your products. How is it going to affect your reactants? So they're basically asking you, if you're increasing the products, it's going to favor the reverse reaction, and that's going to mean that your reactants will increase. Why does it happen? Because the Chatelier states that by increasing the products, the reaction will want to balance the scale again by decreasing the products and increasing the reactants. Does that make sense to everyone? Okay, so do you guys see how to approach all of these questions? Always think about it logically. Try and think about it as a balancing scale. If you tip the scale to the one side, you're going to do whatever you can to tip it back so that it's balanced. With these type of questions, they're trying to see whether you actually understand the theory. So do you know that at the point where your concentrations are staying constant, that's when you're in equilibrium? And in the previous one, when they gave you the graph, do you know how to read off of graphs? Things like that. So with this, it's basically a lot of theory and just thinking about things in terms of what's going to happen if you do this, how will you be able to make it go the opposite way. So that's chemical equilibrium in a nutshell. Tomorrow we'll be starting with electricity and doing that for the rest of the week. Hope to see you guys tomorrow. Enjoy your day.